Hey Chem Nerds, it's Miss Dooley here. This is a review video for my classes, but this is also a video because Miss Diaz has pink eye. That is not her eye, but that's kind of sort of what I'm envisioning it looks like. So she is definitely not here today. So we thought it would be a good idea to make this video so you guys wouldn't get behind. And if you need to go back, because there's a lot of steps in what we're going to do today, you can always go back and watch this again. It's going to be posted on my website. So if you log on to the Haltom website and go to Miss Dooley's page, over on the menu, you're going to see where the pre-AP section is. If you click on the pre-AP section, it will be listed in the pre-AP Unit 7 nomenclature folder. It also will be on my YouTube channel, and I'm going to remind 101 all of my students as well. I'm assuming once I send this to Miss Diaz later in the day, it'll show up on her website at some point in the next day. So if you need help, I am here after school today until 4, and I'm also here tomorrow after school until 4, just in the event that she's not here again. So go ahead and grab your mole sheet that you took example notes on either yesterday or the day before when you were doing train tracks with ions and maybe atoms in a mole problem. We're just going to do 2 more examples because we think you need to see this in order to be successful on the mole homework that you received. So I do this weird little molar roadmap, I call it, and it looks like this. Little Mercedes symbol. And liters lives up here, grams lives down here, moles lives in the middle, and in a compound, this would be either FUs or molecules. And then this week we're learning how to extend that down and tear these apart into ions or atoms. And so I like this because it's really visual and it tells you how many steps you're going to need before you even start your problem. So let's look at the problem. Let's see what they gave us. They gave us 5.5 moles. And so on my map, I'm going to start here at moles. They're looking for nitrate ions. They're very specific here. This is how this example is different than yesterday's. They're very specific about which ions they want. They don't want all of the ions in barium nitrate. They just want the nitrate portion. And I'll show you how to do that in just a second. And so I'm still going to ions. So I go down to my map and I circle ions. So if I wanted to figure out how many steps it's going to take me to get from my given to my end result, I start here with the given, which was moles. That's going to be my step 1. I'm going to have to trek down here to FU and molecule. That'll be my step 2. And I'll finally arrive at my destination down here at ions, which is step 3. And so I can come over and I can draw 3 train tracks, and I'm all set up and ready to plug in, and I'm ready to go. So I plug in my given, which is 5.5 moles. And of course, we need a chemical in that box. Our chemical is barium nitrate. So I'm going to come up here and write that formula. Barium is a +2 charge. Nitrate's a -1 charge. We crisscross. There we go. So we've got barium nitrate. So I might do this a little bit different than Miss Diaz, but this is what I tell kids when you're learning. This makes you faster. And I want you to not only know it, but I want you to know it quick. And so after we left moles, look where we went. We went down here to formula units or molecules. So you have to ask yourself, is this a formula unit or is this a molecule? So when you look up here and your first chemical is a metal, it's a formula unit. And so I tell my kids to remember, FU, metal. And so metals are always formula units. So we're going to go from moles to formula units of barium nitrate. And after we leave formula units, we're going to go down here to our destination of ions. So I do that next. I'm going to leave formula units, and I'm going to come down and land on ions. But this is not ions of barium nitrate. This is really just ions of nitrate. So you really have to pay attention to the detail here. And then we're going to put nitrate in that box instead of the entire formula. And you'll see in a minute how this changes everything. So, this grams is in my way. And so then we do the diagonal thing where we say moles of barium nitrate come down, FUs of barium nitrate come down. And what I like to do is look for the things that I'm confident that I know for a fact. I know for a fact every time I write the word mole, I'm going to include the number 1. So I'm going to come over here where it says mole, and I'm going to give them a 1. You should know at this point that 1 mole of a substance is equal to 6.02 times 10 to the 23rd formula units. Now we get to our new step right here. And so we've got to come up with a relationship that is true for our compound up here, barium nitrate. When we put chemicals into water, they ionize or split into ions. So if we put barium nitrate into water, what would happen is it would split right down the middle right here. When that happens, you're usually counting, saying, yes, there's 1 barium ion. And then you're keeping the nitrate totally intact and saying, how many nitrates would break off? And that's where that 2 is your answer to that question. If they were asking me about barium nitrate ions, the answer would be 3. But since the formula or the given is asking us for nitrate ions, we're going to put a 2. So there are 2 ions in one formula or in one formula unit. So in one compound of barium nitrate, there are 2 ions. And so then we get an answer. Sig figs are always our favorite. 6.6 times 10 to the 24th ions of nitrate. All of that needs to be included on your answer. Don't skip out and leave off your letters and numbers. You really need all of this in order to be successful. Now, truly, this is called dimensional analysis. We want you to go back and check that you analyze your dimensions properly. So I'm always looking that this box always matches its diagonal, and it does. And if it does, I can cancel them out, which means I've converted moles to FUs successfully. I do the same thing here. My FUs match my FUs, so I can cross them out. And so what I'm ended up with is ions of nitrate. That's what I wanted down here. I'm good to go. Last mole example, and then we're going to switch gears. Now we're going to ask how many atoms are produced from 89.3 grams of iron 3 oxalate. So again, if we went up to my little map, we are starting at grams, which is down here, and we are going to atoms, which is now down here because we're dealing with compounds. So if we had to count and number, this is step 1, step 2, step 3, step 4. So I'm going to need 4 tracks. I put my given in the first box, 89.3 grams. Iron oxalate, iron, Roman numeral 3. Oxalate's that weird one that looks nothing like its formula. They crisscross. So we're going to put that in our given box. After we left grams, we went to moles of iron oxalate. After we left moles, in step 3, right here, up on our map, this is our FU step. Since iron is a metal, FU metal, and we're going to go ahead and put FUs of iron oxalate. Trust me, I know, writing iron oxalate this many times in a row is annoying. And then finally, we're going to get to our last step, which is atoms of iron oxalate. Sorry for the handwriting. It's nasty, I know. So then we diagonal down. I'm going to save some time and skip out. There's some grams. There's some moles. There's some FUs. No, you may not do this. You have to write all the little letters. I know it's annoying, but it'll pay off big time later. So then I analyze my track and I try to figure out what numbers do I automatically know. Well, I see moles and I see moles. Easy peasy, they get a 1. I see FU here and here. So I get to use 6.02 times 10 to the 23rd, but I can't put it in both places like I can with moles. So you have to figure out where would it make the most sense. Where would it make a true statement to say 6.02 times 10 to the 23rd FUs is equal to 1 mole. So that means we're going to put it up here. 6.02 times 10 to the 23rd. Then I'm going to go back down here and I'm going to find my grams of iron oxalate by calculating his molar mass. And his molar mass, I did it on the calculator ahead of time, is 375.744 grams using the periodic table and multiplying by each individual. Just to point out, there are 2 irons. There are 6 carbons because you have to multiply by 3. And there are 12 oxygens. So that leaves me to our new last step down here. So they're wanting us to analyze this formula unit right here and say, okay, how many atoms are in there? So what we get to do is we get to put a 1 down here because it's 1 unit or one chunk of this compound. 1 formula unit has how many atoms? Well, we kind of just did it down here at the bottom. We said it had 2 iron atoms, 6 carbon atoms, and 12 oxygen atoms, which equals 20. So we're going to put a 20 on top of that track. We cancel our grams, we cancel our moles, we cancel our FUs, and what we're left with is 2.86 times 10 to the 24th atoms of iron oxalate. So that's all for this example. We are going to switch gears. So grab the paper that you should have grabbed on the way in. There were 2. One is just called Empirical Formulas, and one looks like a homework sheet. Indeed it is. All right, so I'm on the one that so looks like this at the top. So see if you can't locate this one. I don't know what page number it is in Miss Diaz's class, so you'll have to ask her when she gets back. But rather than you taking your own notes today, I went ahead and pre-printed some notes so it would be easier to follow along. So we're going to calculate some empirical formulas. Imagine you worked for a pharmaceutical company. Would it be okay to say, this formula's kind of sort of right. We're going to put it into this medicine and feed it to a bunch of humans? Well, of course not, because how do I know if it's contaminated? What do you mean it's kind of sort of right? Empirical formulas kind of deal with the purity of a substance. And what scientists can do is they can identify some unknown substances based on what they find out in a lab. So they run some experiments and they get some data and they figure out some percentages of all of the different things it could be in this chemical. And from that, they can determine what the mystery chemical is. It's kind of cool. So the word empirical formula here means the lowest whole number ratio for the elements in a compound. We kind of call this the reduced version. So you may want to underline and add the word reduced. And then it says this may or may not be the same as the molecular formula. So sometimes the empirical and the molecular formula are the same. Sometimes they're different. We kind of refer to the molecular formula as the inflated version. So look at the examples that you have in your notes. It gives you water. Water is both an empirical and a molecular formula. Let me tell you why. Can you take the numbers for water, which is a 2-to-1 ratio, and reduce it? Well, of course, the answer is no. So because it's already in its simplest or lowest form, he's called the empirical formula. We also use water all the time. It's everywhere we go. We should be drinking an insane amount of water a day. I try to drink 100 ounces a day. But because we use water in this form, it's also called the molecular formula. So this is kind of the practical version of a chemical. So if we look at this second example, this is H2O2. This is hydrogen peroxide. If you drink it, you'll die. So here's my joke. A man walks into a bar and says, "I'll have an H2O." A second guy comes up to the bar and says, "I'll have an H2O too." And he dies because he drank peroxide. So peroxide, is it in its simplest form? The answer is no. So it's inflated. It's doubled. And so because it can be reduced, it's called the molecular formula. So if we wanted to take peroxide and reduce it, the 2's would reduce down to a 1-to-1 ratio, and you'd end up with HO. HO is the empirical formula for peroxide. It is not the practical version that we use every day. This is hydrogen peroxide. This is the empirical formula for peroxide. So they are different. We listed the steps in your notes for you just to save some time today. And so you've got steps to calculate an empirical formula. Remember yesterday or the day before, we calculated percent composition, and I gave you potassium permanganate. And I said, I want to know what percentage is K, what percentage is Mn, and what percentage is O. And you came up with all these nice little percentages for us. Thank you very much. It was like so easy. Well, empirical formula is kind of like the backwards version of a percent composition formula. We're going to start with a percentage, and we're going to try to go backwards and create this chemical formula from our percentages. So it's kind of like solving a mystery puzzle. And so look at step 1. It says we're going to change our percent into grams if necessary. If I give you grams, you obviously don't have to change the grams to anything because it's already in the correct format. So if I gave you 79.8% carbon, all we would do is drop the percent and slap a G unit on the end. We're assuming that there's 100 grams of the chemical because we assume that there was 100% of the chemical as well. So step 1, you literally drop the percent, slap a G on it. Step 2, you're going to convert grams to moles. Quick little train track. Step 3, I would highlight it. It is the step everybody forgets. So we're going to divide by the smallest number of moles. We'll talk more about step 4 right here when we get to 1 because it won't make any sense at this point. And then we're going to write new chemical formulas with our subscripts, and that'll make a lot of sense too when you see the example. All right, so here's our first example of an empirical formula. So in step 1, it says to take the percent and change it to grams. Watch this, it's fancy. G. So I'm done. So I did step 1. Step 2 says let's convert those grams into moles. So I'm going to start with 79.8 grams of carbon and go to 20.2 grams of hydrogen, and I'm going to convert to moles. There are 12.011 grams of carbon in a mole and 1.008 grams of hydrogen in a mole. Now at this point, your brain might be thinking, wait a minute, this is a diatomic Hofbrinkel. So we're supposed to double hydrogen. We're only allowed to double hydrogen when he's alone by himself. Well, we're about to make a chemical formula out of carbon and hydrogen, so they're going to be connected. So in a formula, he is not a Hofbrinkel, so we don't double him. This is the only instance all year where we will tell you, don't double your Hofbrinkels. And so once we do that, we are going to put it in our calculator, and we are going to come up with our moles. 6.64 moles and 20.0 moles. Step 3, step 3, step 3. It's the step everybody skips. Divide by the lowest number of moles. So who's the lower number, 6 or 20? Obviously, it's 6. So we're going to divide both of our moles, both, by the lowest number. 6.64, 6.64. This cancels out, turns into a 1. When you put this into your calculator, you get 3.01. So here's a question. Would you assume that 3.01 is close enough to 3 to just round it, or do we need to do something special? Well, we have a rule for that. So write this down somewhere, either on your example 1 or up at the top of your page. So let's assume this is a number line. And this right here is a whole number. So if I were in front of your face, I would say, hey, pick your favorite whole number. Somebody earlier picked a 7, so let's pick a 7. So we can go up. This is 0.05. This is 0.10. This is 0.15. We can go up all the way to 7.15. And when we look at that number, we say, is that close enough to 7 to round it to 7? And the answer is yes. So we're going to round anything in this range right here down to the nearest whole number. So 7.15 would round down to 7. If we had 7.07, right about here on the number line, we could round that down to 7 because it's in this range. Same thing on the bottom side. This would be 0.95, 0.90, and 0.85. So we can go down to 6.85 and analyze that number and say, is that close enough to round it to 7? And again, the answer is yes. So I can round this side up to the nearest whole number. So 6.85 would round to 7. 6.93 would round up to 7. So because we've got 3.01, the only thing that changes here is that instead of being a 7, is that the whole number is a 3. Is 0.01 in the range? Yes, it's hovering right here next to the 3. So this guy is close enough to round. So we mark that out and say that's a 3. The whole goal in an empirical formula is to end up with whole numbers, and we did. Hooray! Now, something to note, when we're about to write our chemical formula, we do not need to use step 4 because we had whole numbers. So we skip to step 5 where we use these mole ratios in order of our subscripts. We go in the order that they were given in the problem. Since carbon was given first, we write C. It's an imaginary 1. So there's a 1 down there, but we're not going to write it. Since hydrogen comes second, we're going to put an H next to the C. And we look down and say, oh, well, there were 3 moles of that, so we put a 3 on the end. So this is a mole to mole ratio. And so when these all hook up, it makes this chemical formula of CH3. You cannot reduce it, so that's why it's called the empirical formula. So that's the first example. It's not that it's hard, it's just that there's a lot of steps. And if you forget this step here where you divide by the lowest moles, then it's a train wreck and it's really hard to figure out. Let's try another one. All right, our second example is a little bit different. So you might notice automatically I gave you grams. And when I give you grams, you get to skip step 1. Sweet, saved you a step. But it was an easy step. Second step, we're going to change our grams into moles. Molar mass off the periodic table. Do the same thing for oxygen. Again, since oxygen's about to be in a compound, he is not a Hofbrinkel. So we're not going to double the 15.999, but you should have on the homework. Oh yeah, obviously the homework's not due today. Yay! So because of the CTE fair tomorrow, both of your homework sheets that you have, your moles and your empirical formula, Ms. Diaz is going to want to see on Monday. So you can come to tutorials today or tomorrow after school and ask me questions before Monday. And that's equal to 1 mole of oxygen. So after some speedy calculating here, I come up with aluminum as 0.1538 moles and oxygen as 0.2308 moles. So we do step 3, which is divide by the lowest number of moles. So we're going to divide by 0.1538 because it's smallest. And our calculator answers look like this: 1 and 1.5. So look back at that number line. Well, we got a 1, so there's a whole number. But this 1.5 is going to be problematic because I can't get that into a whole number because it's too far away. It's out of the range. 0.5 is not between 0.850 and 0.15. It's too large because this is really a 1.501 in the calculator. So I can't round this. So if you look at step 4, it says if you don't get a whole number, you have to multiply by 2, 3, 4, or 5 until you do get a whole number. And so this is the way I look at it. I say 1.5 is really like saying 1.5. What's the reciprocal of this fraction is 2. So I'm going to multiply this guy by 2. And when I do that, it's going to turn into 3. So there's my whole number. But if I multiply this subscript by 2, I'm going to have to go back up here and do the same thing to the 1. So the 1 also will get doubled and turn into a 2. So I've got a 2 as a subscript and a 3 as a subscript. So I come down here and say aluminum. There are 2 of them. Oxygen, there are 3 of them. That is my empirical formula for this mystery compound. So what if it had looked different? What if it had come out as this? 1.34. Multiplying this by 2 would get us 2.68. That is not within the range to round. So multiplying by 2 didn't work. Another way to look at this is 1.34 is really close to 1/3. So if we did the reciprocal trick, we're going to be multiplying this guy by 3. And when we do that, we end up with 4.02. Now this guy's in the range, and I can round to 4. So you're going to keep doing that. And so if you don't understand the fraction rule, don't worry. Just take the weird number that you get and start multiplying. Try 2, see if it works. If it doesn't, try 3, see if it works. If it doesn't, try 4. And if it doesn't work, try 5. If none of it works, there's an error in your calculation because I promise one of those will get you within the range that you need to round. All right, now flip over the notes page onto the back. Let's talk about molecular formulas. This part's pretty easy. A molecular formula is the actual formula. Like we said earlier, it's the inflated version of the formula. They may or may not be the same as the empirical, or it's a multiple of it. So in biology, you learned this guy, C6H12O6. This is obviously the inflated version of a formula. If we wanted to make it into an empirical formula, all we would have to do is reduce. So the 6 would become a 1, the 12 would become a 2, and the 6 would become a 1. Obviously, we don't write the 1s. So this would be my empirical formula. So we could say that going this way, we divided by 6. But if we wanted to reinflate that, we would have to multiply it by 6. That's all we're about to do. Super simple. So if you look at the next example, it's really super nice. Look, they did the hard part for us. They said, hey, I've got this compound. The empirical formula is P2O5. So I've got this white powder. So here I'm gonna draw a sample of my white powder. So draw a blob on your notes that looks just like that. This compound has a molar mass of 283.9 grams. What's the compound's molecular formula? Well, there's a possibility that it could be dihydrogen pentoxide. We have to analyze to see. And the way we do that is finding the molar mass for this guy. So when I add up the molar mass for diphosphorus pentoxide, I get 141.943 grams per mole. Well, when I investigate and I compare this number to this number, obviously they're not the same. Some of you have a ton of common sense and you can automatically see what we're going to have to do to get from 141 to 283. But if it's not so obvious, always take the big number, divide by the small number, and see what you get. So if we took 283.9 and divided by 141.943, we actually get 2.00. So basically what this is saying is, hey, multiply by 2. So we're going to inflate this and double it. So we have to do the same thing to our formula, which means that our molecular formula for this mystery white powder is P4O10, tetraphosphorus decoxide. That's how you do a molecular formula problem. How could we ruin your life? We could make you do both at once. So let's try it. Last example for the day. Down at the bottom it says a compound is used as an additive for gasoline to prevent engine knock, and it shows the following percent composition. So it lists out your percentages. So we're going to take our percentages and change them into grams. This time there just happens to be 3. That's the only reason that this one is a little more overwhelming. We do our molar masses. When you've been doing this for thousands of years, you have these memorized. I'm like a dinosaur. And then we calculate. So the answers I get in my handy dandy calculator are 2.021 because I love sig figs, and 2.021, isn't that weird, and 4.038. Now, at this point, your brain is probably thinking, oh, there's our ratio, 224. But don't forget, divide by the lowest number of moles. Got to divide. It'll ruin you. Divide by the 2. And And when we get that, we get a 1, a 1, and 1.998. Is that close enough to round? Absolutely. So it's a 2. So our empirical formula will be ClCH2. But we haven't answered the entire question. It says determine the empirical and the molecular formula. So they want both. So they want us to inflate this. Well, it didn't say to what. Well, it kind of did. Look at the clue. The molar mass is known to be 96.96 grams. So we want our mystery compound to equal 98.96 grams. Don't worry, it was just Giovanni Escobar. That explains everything. So if we want our mystery compound to equal 98.96, first we have to figure out what does our compound equal. So we go back to our empirical formula, ClCH2, and add up the molar mass. And we find out that it's 49.48 grams. And so from that, we realize that obviously these two numbers do not match. So you could take 98 and divide by 49, and you can figure out that we're multiplying by 2. And so we're going to take our empirical, I'm going to do it up here, and we're going to double it. Cl2, C2H4. It's a lot of work, but it's not necessarily that hard. Just keep in mind that fraction rule, that if you end up with some weird numbers, you can multiply to get rid of those fractions so they're in our range on the number line. Have a great day. Hope I didn't fry your brain. Don't forget to come to tutorials. We'd love to see you. Thanks, bye.